Today we're going to look at what happens when you add 2 to an x value within a function. First we have f of x equals x plus 2, then we have f of x equals x plus 2 quantity squared, and finally f of x equals the square root of x plus 2. The key here is plus 2, and the name of this lesson has to do with horizontal shifts. So we're going to see why this shifts horizontally when we add 2 to the x values. Here we have our first function, f of x equals x. I want you to notice what happens when I add 2 to the x value, and we're going to call that c, and you'll see why in a little bit. When c is equal to 2, notice what happens. The green function f of x shifted 2 to the left for my parent function p of x equals x. Why does that happen? You would think it would shift to the right. Why does it move to the left when we make c equal to plus 2? Well, that's what we're going to find out. Right, let's look at f of x equals x squared. Again, we see that when we make c equal to 2, the green function f of x moves 2 to the left from the parent function x squared. So again, why does it move 2 to the left if c is positive 2? Again, we're going to find that out in this lesson. Finally, let's look at f of x equals the square root of x. Again, we're going to make c equal to 2. And we're going to notice that when c is equal to positive 2, the green function f of x equals the square root of x plus 2 moves 2 to the left from p of x equals x square root of x, or x to the 1/2. So why does that happen? Why, when c equals 2, positive 2, does the transformed function f of x move 2 to the left from the parent function? Well, we can see that when c is equal to positive 2, the parent graph shifts to negative 2 units to the left, I should say. Okay, so why does it shift 2 units to the left when c is equal to positive 2? Well, let's look at this numerically. If I plug in 0 in for x squared, so let's go back to our x squared function. Okay, so we're trying to figure out why this shifted 2 to the left when c is equal to positive 2. And let's look at this point 0, 0. It went from 0, 0 to negative 2, 0. But why? Well, if I plug in 0 into my parent function, I obviously get 0 back, right? Well, in order for me to get 0 back again with my x plus 2 transformed function, I would have to plug in negative 2 to compensate for that. So if I plug in negative 2 into my transform function, I get negative 2 plus 2, which is 0, and that gives me the exact same y value back of 0. In other words, I had to plug in an x value that was 2 less from 0 in order to get the same y value back of 0 back. Therefore, my x value went from 0 to negative 2, and therefore my horizontal shift was negative 2. In other words, it shifted to the left 2 units. Again, we can see this here graphically went from 0 to negative 2, even though my c value is plus 2. In other words, I had to plug in the opposite of positive 2. I had to plug in negative 2 to get the same y value. Let's look at a different point. Okay, we're going to use the same function x squared, but this time we're going to plug in 3 to our parent function. We're going to get 9 back. Let's go ahead and do that. I'm going to change my zoom here. So notice what happens for my parent function. Let's just shift this back for a second to 0. When I plug in 3, I get 9 back. Why? Because 3 squared is 9. Now let's look what happens when I again make c equal to positive 2. Notice that the function shifts to the left again. Now the question is, what number do I have to plug into the green function, the transform function, to get 9 back? Well, it looks like 1, right? If I plug in 1, I get 9 back. In other words, it shifted 2 to the left with the same point. So let's look at that numerically and see why that happens. So again, I want to get 9 back from my transform function. In order to do that, I'm going to have to take the 3 that I normally would be plugging in and subtracting 2. That will cancel with the positive 2 that I put on the function. Again, the negative 2 and the positive 2 will cancel, and I'll be left with that original 3 I plugged in to get my 9 back. So in other words, I'm plugging in 3 minus 2 to cancel the plus 2 out. What is 3 minus 2? Well, 3 minus 2 is 1. Therefore, this confirms that the original 3 that I plugged in, I have to subtract 2 from that to plug in 1 to still get 9 back. We can see that again with this graph. Plug in 3 from my parent function, I get 9. I will have to plug in 2 less than that 1 in order to still get 9 back. Another way to show this is that since p of 3 is equal to 3 squared, which is 9, what if I wanted to look at this like an algebra problem, which is what we're actually getting at? I'm going to take my original x value 3 that gave me 9 back. I'm going to set that equal to my new transformed function x plus 2, which is inside of the squared. So in other words, if 3 is equal to x plus 2, if I can solve for an x value here, that will ensure that I get the same y value back of 9. So I'm going to set 3 equal to x plus 2. Well, if 3 is equal to x plus 2 and I subtract 2 from both sides, you can see what's happening here. You can see why the horizontal shift is minus 2 to the left, because I have to subtract 2 to cancel this 2 out in order to solve for my x value. In other words, my x value is going to be equal to 3 minus 2, which is 1. So therefore, x equals 1 is the value that I need in order to ensure that I get the same y value back of 9. We'll see that down here below. So my original parent function, when I plug in 3, I get 9 back. Okay. My new transform function, I have to plug in 1. In other words, I have to take my original 3 and subtract 2 from it, and that will ensure that my 2's canceled. 2's cancel, and I get 3 squared, which gives me the same y value of 9. So if I subtract 2 from my original x value, I will get f of 1, which still gives me 9 back. Again, we can see that with the graph here. F of 3 is equal to 9. F of 3 minus 2, f of 1 is also equal to 9.